So welcome to lecture 27 of MCS 471, an introductory course to numerical analysis. And for today, in particular on numerical integration. So this is our third lecture on numerical integration, but it is self-contained. So we ramp up quite slowly, with again explaining the notion of what is a quadrature rule and how we can determine the accuracy. What is a good rule? So in numerical analysis, our first concern is for accuracy. And we have one symbolic method to compute quadrature rules. That's the method of undetermined coefficients. Very good. Then how the central question for today is if we can determine, if we are completely free in determining where we're going to evaluate our functions, what is the highest degree of precision that we can get at? So that's the question that we will solve today. Accuracy improves with orthogonality. So we have encountered orthogonality already at least twice when we talked about the approximation of functions and also when we solved linear systems. So orthogonality here will actually be used to solve that question. So that's the main point of today. We use orthogonal polynomials, and we will get highly accurate quadrature rules. So at the last part of this lecture, I will introduce the reduction to an eigenvalue problem. With today's technology, doing hundreds and thousands of evaluation points is no longer really a problem. So how do you then fabricate Gaussian quadrature rules in a very efficient manner? So the method of determined coefficients is fine if you work by hand, but you don't want to do this for 100 and certainly, well, even not for 100. So as soon as things start to get larger, what is necessary for applications, then you actually need to use linear algebra. And that will be the third part of this lecture. So let's dive in. So how do we construct quadrature rules? Well, first of all, what is a quadrature rule? So here's the problem. We have a function defined over an interval AB that we can evaluate, and we want to approximate a definite integral by a weighted sum of function evaluations. So we are using interpolation again. So all the points need to be distinct from each other. So the question is, where are we going to evaluate? And then also, what are the weights? So this is our numerical problem. It's a slide that I took from 2 lectures ago. And then actually I pointed out that we started here counting at 1. And with interpolation, we start at 0. A polynomial of degree n has n roots. So counting from 1 is again a lot natural here. So in a way, with the framework of Gaussian quadrature, we think about roots of orthogonal polynomials. This is a numerical problem, and with every numerical problem, we ask ourselves first, what is the difficulty of the problem before we get into the accuracy question. So this is also something that we will try to tackle here. The function is defined over an interval, but sometimes it is not. So some functions and we covered this already with Romberg integration, some functions are kind of difficult at the points in an interval. So they may not be even everywhere defined. So the problem becomes ill-conditioned or difficult or ill-posed even if you have an asymptote, if the function somehow shoots off to infinity. So we will see how we can reformulate those problems. So the standard tool in our box is reformulating. Gaussian Quadrature can also actually deal with difficult problems. But let's first work on the accuracy. So first, when we solve a problem, we try to think about what are the nice instances. And here, what are the nice instances? So these are the polynomials. If we can polynomials, and we know how to do this algebraically, polynomials have very nice antiderivatives. If our rule integrates all polynomials up to a degree, then we say that this test has this degree of precision. Again, so we actually don't have a backward error here with area problems. So we work with test problems. And our first class of test problems, they are the polynomials. So the degree of precision is an important concept, so it's highlighted here. But think about also the issue, what kind of test problems we can solve correctly. So in a way, what we're doing now in the second part of this course, we are going to apply ideas of interpolation, but we apply them to problems that are actually a lot harder. The nature of quadrature has a much higher complexity than, say, linear system solving or nonlinear equation solving. All right, let us see the method of undetermined coefficients. Here is a problem. So we want to compute the integral of a function. The integrand is defined over a symmetric interval minus h plus h. And we want to evaluate at minus h, 0, and plus h. So we have actually not much choice where to evaluate. So the method here is applied to a very specific setting. We are going to require essentially with 3 points. So this is interpolation again. With 3 points, we can uniquely determine a quadratic polynomial. So we expect to have an integration formula that can be correct for every quadratic polynomial. So the integral is a linear operator, so we integrate the standard basis functions. We do this symbolically, our right-hand sides. So some of the weights, so the weights are now formulated as A, B, C instead of W1, W2, W3. So the sum of weights needs to equal the length of the interval. That's actually always something that needs to happen. Then we have kind of a symmetry relationship. So the second equation will actually respect the symmetry. So you can kind of see already that A and C have to be the same. And then we have an extra condition. So we have 3 weights. We will have 3 linear equations that we then solve. And we actually did this already. So this is Simpson's rule, but now seen in a different setting. Here we did it by hand. So the equations can be solved. So the second equation states that the first weight is equal to the second. And we can eliminate from there. And this rule will integrate every quadratic polynomial correctly. So it is formulated with minus HH. So there is a standard notation. The standard interval is minus 1, 1. And we can always scale then to whatever interval we want to formulate the rules. All right, the midpoint rule again. So the midpoint rule is a rule where we started with. And this is an exercise that you solved already 2 lectures ago. But here we solve it again, pretending that we don't know the midpoint rule. So what is the exercise? The exercise says that we have an interval AB, and we want to determine an integral, a quadrature rule, with only one point. We don't know where to evaluate that point yet, so suppose that we don't know the midpoint rule. Determine the weight and the point where we interpolate so that the degree of precision is as high as possible, pretending that we don't know the midpoint rule. So the midpoint rule, once again, we've covered this already. So last time we said very bad things about the midpoint rule, but here the midpoint rule is the first example of a Gaussian quadrature rule, as we will see. So it is a very important example. All right, here is another exercise. So in this part of the lecture, I want to emphasize that the method of undetermined coefficients is a very important method. So here is another quadrature rule, framed now with A instead of H, and you have only 2 weights, and we have actually specified where we're going to evaluate our points, minus H, minus A and A. So the expected degree of precision will be 1. We will expect that every linear function is integrated correctly. Although here, for solving that exercise correctly, you also should check the quadratics. So you may have, and the point of this lecture will be that you can do much better for if you can choose your interpolation points better. So this is coming back to interpolation. How can you get the smallest error possible if you can determine the interpolation points? All right, so that's the problem. That's the problem that we will solve in this lecture. We are integrating by interpolation, which means that we will construct an interpolating polynomial and then take the value of that integral of the interpolating polynomial as the approximation for the integral. So perhaps should I underline something? Perhaps yes. So let me do that. So if we want to interpolate, what is actually now the main point of this lecture? Well, it's not the main point of the lecture. What is the main point of quadrature rules? We construct an integral, we construct an interpolating polynomial, and we integrate it. All right, what is the error now? So we want to integrate polynomials of higher degree. Well, suppose that we have a polynomial of higher degree, then we can write that polynomial as in terms of the polynomial of lower degree by the long division. So we will divide our polynomial by a polynomial of degree. So we have a quotient. So let me try to explain that again. So we can write any higher degree polynomial as the interpolating polynomial plus a quotient with a remainder. So the notation is a little bit off. So the interpolating polynomial is actually Q, is our divisor. And the Pn is actually the remainder. And how high can we take the divisor now? So the R contains the extra degree. So the polynomial f will have the degree n plus k. We don't know yet what the k is. So how high can we take the k? That's the question. How high can we take the k such that the quadrature rule will integrate any polynomial f correctly? All right, so we have written this higher degree polynomial as f equals p plus q times r. Now, the integral of p is our quadrature rule. The integral of q times r is the error of the quadrature rule. So we want that error to be 0, and that will lead to conditions on the Q. So it's, again, we are essentially applying the same idea where we started with the method of undetermined coefficients, exploiting that the integral is a linear operator. So we have necessary and sufficient conditions on the Q. And that's the Q that we use in the representation of the polynomial. And remember again, what is the Q? The Q is the product of all the x minus xi's. So it's actually the error term in the interpolation. So the interpolation had one important error term that was the wobbling interpolation term when we looked at the problem of approximation. All right, we are almost there. So orthogonality will make its entrance now. In a way, we solved this problem already. We introduced the Chebyshev interpolation, and Chebyshev will come back again. So by using orthogonality. So we can interpret the conditions as an orthogonality requirement. So the integral operator satisfies the requirements for an inner product. So we have an unknown polynomial. So the polynomial has n plus 1 coefficients, but the polynomial is actually determined up to these leading coefficients. So it's actually primarily determined by its roots. So the main result, the main theorem here is that if you look at the determination of this problem again, it's a linear system in the unknown coefficients. We are solving essentially an interpolation problem again. So we want to determine the the two last lines are actually theorems that we have seen already. So, and I mentioned a specific example. A quadratic polynomial is determined uniquely by 3 points. Here, if the degree of Q is 2, then the highest that we can go is 2 minus 1. And actually the conclusion is that the k, the unknown k, for the polynomial f to be integrated exactly is 2 times n minus. So the highest k is n minus 1. So we can already integrate the first n basis functions. So the highest degree we can go is 2n minus 1. And that is actually the main point of this lecture. So let me try to highlight that again. So I will highlight the main point where we have the main theorem here stating that if we are using orthogonal polynomials, and this is the orthogonal condition here, we can reach a precision up to 2n minus 1. So polynomials are uniquely defined by their roots. So that's the geometric way of seeing it, while we will interpolate at roots of polynomials. So again, we did this already when we considered Chebyshev interpolation. We took the roots of the Chebyshev polynomials. So in this lecture, we will consider two of the most obvious and general Gaussian quadrature rules, Legendre and Chebyshev. We have seen Chebyshev polynomials already, so I will spend more time with the Legendre, Gauss-Legendre integration, which is determined by the interval -1, 1, and for which there is a 3 terms recursion. The Gauss-Chebyshev quadrature rule is a little bit funny because it uses this weight function. And perhaps then when we introduced Gauss-Chebyshev polynomials, this weight function also occurred, but that was kind of unnatural. Here we can use this to our advantage. Remember the square root of 1 minus x squared with Romberg integration? That was kind of a very unexpected and tricky thing. Here actually what we will do with improper integrals, we will actually be able to integrate functions that have a very strange behavior at the endpoint. So Gauss-Chebyshev quadrature is very good at treating improper integrals, where the endpoints of the integral are actually not well defined, for functions that are not well defined. So that will be the endpoint also why we would consider. So this is actually another reason why you may want to consider Gaussian quadrature if you have to deal with improper integrals. And that goes back to the conditioning problem. So we actually are reformulating then the problem. If we have an ill-conditioned problem, we are reformulating it. So what do you do when you have an asymptote, when the function is not defined in the middle of the interval? If you want to have to integrate 1 over x with an interval that contains 0, well, you simply split the interval then in 2. So you reformulate the problem. That has been our standard answer whenever we have an ill-conditioned problem. We don't solve it, we turn it into another problem. So Gaussian quadrature is actually also doing that. All right, how do you do things now? Here are 3 simple steps to make Gaussian quadrature rules. We construct orthogonal polynomials up to a certain degree. We compute the roots. So these are then the interpolation points of the roots. And we use the property that the weights of interpolating quadrature rules are the integrals of the Lagrange polynomials. So the root finding problem we will do with companion matrices for linear algebra. The construction of orthogonal polynomials follows from a 3 terms recursion. Gauss-Legendre quadrature, I will use that as the running example. As the exercise, running exercise here, you will do it with the Chebyshev polynomials. So how to construct now the interpolation points? Well, we look at the Legendre polynomials. and this is a 3 terms recursion. We could do this with a recursive algorithm, but for most efficient way to do this would turn this into an iterative algorithm. So here is the iteration. We compute a sequence of Legendre polynomials. So we can see this algorithm in 2 ways. We can see this as a symbolic construction. That's how we will be using it first in a first attempt to construct the Gauss-Legendre rule. So the x is the letter x, is the symbol x. But very importantly too, this is an algorithm to evaluate the polynomials. So the x can be a number. So how do you evaluate a polynomial efficiently? This goes back to the very, very early beginning, the fundamentals in this course. We can evaluate every polynomial of degree n with n multiplications and n additions. Here you see that this is also an algorithm that evaluates the Legendre polynomials in a linear cost. So you can count the number of multiplications and the number of additions that you have to do. So cost is very important. The other important aspect here is the accuracy. As will become clear in one of the exercises, this is also the algorithm that you must use to evaluate the Legendre polynomials. All right, so let us do this first symbolically. So there is a Jupyter notebook that is posted at the website. There are also some Julia programs. We will first work symbolically, and the x is our symbol for the variable. And here we have the 3 terms recursion that is worked out as an iterative algorithm. In perhaps a digression here, if you have taken Introduction to Symbolic Computation, then you can still use the 3 terms recursion if you memoize the recursion. So if you have a dictionary to store the entire table, and then it can be done efficiently with lookup. Otherwise, this is the original 3 terms recursion will give you an exponential cost if you do it naively. But the most efficient way to do this is via the simple iteration here. So that will return you 1 Legendre polynomial, the Legendre polynomial of the degree d, but it will actually also compute a whole sequence of Legendre polynomials. All right, here is how these Legendre polynomials look like. So the 3 terms recursion is interesting, so you can kind of see the shape. So not all coefficients are there, so sparse structures matter. This is a picture of the Legendre polynomials that work for small degree. So you can kind of see the blow up in the coefficients as well. We will use the construction for the first 3 steps, the first 3-step process on how you could construct, following the theory, how you could construct Gauss-Legendre rules of a small number of points. So this is a very good way to do this for small degrees. All right, it's also a symbolic numeric computation. So we are preparing the symbolic representation. So we have the symbolic coefficients, but we want to apply a numerical root finder with numerical coefficients. So array comprehensions are very good to turn the symbolic into numerical construction. How do we compute the roots? we have the linear algebra module and a linear algebra problem that computes the roots is also an eigenvalue problem. So for every polynomial, we can write down a corresponding eigenvalue problem via the companion matrix. So here is the companion matrix for any polynomial up to degree 5. So it's important that there's an honest polynomial of degree 5. We divide out by the highest degree polynomial. So if the input is not honest, if the C5 is 0, then you cannot simply construct the companion matrix. All right, this will be wrapped up into a function. This is a wrapper function. We have the numerical coefficients and we formulate the companion matrix, wrapping the eigenvalue computation. All right, here they are. When we compute, so the numerical representation actually has the advantage is that Julia has the built-in function evalpoly that allows us to compute the backward error. Whenever a numerical routine returns you something, you should always compute somewhere an error. So we are very concerned that not only that our programs are correct, but the difficulty with numerical analysis is that we may have a very simple program that is logically correct, but we do have wrong results. And that will again be a topic of the next exercise. Now for small degree, everything works out perfectly fine. If we print out the errors, which is the backward error, what we get from evaluating the computed roots, the roots of the companion matrix, then you see that we obtain numbers that are close to the machine precision. So actually the point of this slide are the exponent of the errors. And the machine precision is 2 times 10 to the power minus 16. So we are very close to this. So all the roots here are computed fairly accurately. But there is another way to looking at these numbers here. You see that we're working over the interval -1, 1, and look at this. So we have here the number of decimal places that are agreeing. So we have actually also a forward error. So what I circled is the backward error, but the forward error would be exploiting the symmetry. So the roots are actually symmetric. So we have 5 points, and the center point of the interval -1, 1 is 0. So, and we can read this off from this coefficient as well. So you see the constant coefficient is 0. So there are a lot of checks and balances that we can do to verify this computation. All right, this is Gauss-Legendre. The purpose is of the next exercise that you do this with the Chebyshev quadrature rules. So in a very similar way, so in a way, this exercise is a little bit is actually easier than the Legendre function, because you have already here an explicit representation for your Chebyshev polynomials. So you will write, you won't implement this as a recursive algorithm, but you will do a simple iterative function that computes the Chebyshev polynomials symbolically using Sympy. So this is a symbolic numeric exercise. We already know the roots of the Chebyshev polynomials. That was a main result, a main theorem. I think we proved that theorem in lecture 16. So you can compute just like with the previous loop. You can compute the results on the previous slide. You should compute the backward error. But here we know we have an explicit formula for the Chebyshev roots. Assume that, so you also use the roots of the companion matrix, so you can use the same function again. All right, we know how to do Gauss-Chebyshev quadrature. Here is another exercise. So we have our Chebyshev polynomials. We have the roots. Now, do this now not only for 5 points, but do it for 100 points. So we have two representations for the Chebyshev polynomials. One would be the normal representation in the standard basis, 1x, x squared, x to the power 3. But that's actually a very, very bad basis. So orthogonality, for orthogonality, we must use the 3 terms recursion. So the point of this exercise is that you will observe that the roots, even the exact roots, will actually not be very good for the standard representation in the standard basis. So the purpose of this exercise here is that the 3 terms recursion is also a numerical algorithm, and that's the numerical algorithm that you must use to evaluate the Chebyshev polynomials. So you will see that for 100, and if you don't see it for 100, try 200, 300, you will see that the recursive numerical algorithm, so it's not a recursive algorithm, you use the loop in the symbolic form, but now instead of x a symbol, it's a 64-bit floating point number. You will see that the zi's are actually still very close to the machine precision. The yi's start to deviate from this. So this is the loss of orthogonality. The same exercise that we did with the modified Gram-Schmidt. A good numerical algorithm, but you will lose orthogonality in your result. Here also, we will actually lose the exact property of the roots if we are using the expanded basis. All right. Third step, so we have the points where we have to evaluate our functions in order to have a high degree of precision. How do we do this? We could use the method of undetermined coefficients and set up the van der Monde system. Again, if we do this for 5 points, it's very well. But we can do this a little bit better, integrating the Lagrange polynomials. So the roots of so the integrals of the Lagrange polynomials are actually defining the weights of the quadrature rule. So interesting for Lagrange interpolation, we separate the function values from where we evaluate the functions. In some sense, the more new things we do, the more everything stays the same. So the main properties that were so important with interpolation come again here. Here we see the output of Gauss-Legendre program. We see now the complete, so this is kind of a summary of what is Gauss-Legendre integration with 5 points. We see the polynomial, the Lagrange polynomial of degree 5, its numeric coefficients, its numerical roots with backward error, and then also the corresponding weights. And again, the weights, how accurate are they? Well, this is a symmetric formula, so you do have actually have a way to measure the forward error. So here you see I'm underlining now the decimal places that agree. So we have kind of a loss of 2 or 3 decimal places, but that is okay. Our numerical results, if we are losing a couple of decimal places, that is still acceptable. You see that we are using the properties of the rules to verify the accuracy of our results. Good. All right, 2 more exercises again. This is actually work. In the post-it notebook, I took any what I thought of good polynomial of degree 9. So we have the theorem that is stated here again. So with 5 points, n equals 5, so 2 times 5 minus 1 is 9. So any polynomial of degree 9 will actually integrate it correctly. So let's verify this. You generate a random coefficient vector with 10 points. So a polynomial of degree 9 has 10 coefficients. You set up the you apply the Gauss-Legendre rule. So there is a simple function that actually will do this in the post-it notebook. And then you verify, so there is the integrate command of Sympy, that your random polynomial of degree 9 is actually integrated correctly up to machine precision. We have an orthogonal basis. You can verify, so we have symbolic representations for all the Legendre polynomials. Well, use the integrate command to actually compute all the inner products. It's called a Gramian matrix that you compute here. It's a symmetric matrix that verifies the orthogonality of the basis. All right, then I have about 8 minutes left in this lecture. How should this now all happen in practice? So what we did so far was good for low degree polynomials. We can do this for high degree polynomials. So what if you can take 100 points in an interval? Working with orthogonal polynomials always involves a 3-term recursion. Here is a theorem. It's a theorem of Golub-Welsch, but I'm not formulating it properly as the theorem, just the essence here. With every 3 terms recursion corresponds a tridiagonal matrix. The eigenvalues of this tridiagonal matrix are the roots of the orthogonal polynomial. And linear algebra is a very well-developed field. We don't need to compute now the companion matrix. We can just work with this tridiagonal matrix. It's a structured matrix. The coefficients of this tridiagonal matrix are derived from the coefficients in the 3 terms expansion. So computing roots of orthogonal polynomials is solving an eigenvalue problem of a 3-diagonal matrix. And the eigenvectors will give us the weights of the quadrature formula. So that's the second part of the theorem. And this is the general procedure that must be followed to construct quadrature rules where you have several hundred of points. Notice that one does, in this construction here, one does not set up the fully expanded orthogonal, the full expanded version of the polynomials in the classical sense. One does work with the 3 terms recursion to get very accurate representations for the roots. So that is what should be used, and that you will use in the exercise for Gauss-Chebyshev polynomial. So I started out referring to the conditioning of the problems. What are the bad problems? What are the bad inputs? Well, just like with the root point finding problem, there are some very wicked functions that you can give as input. Well, the wicked functions are those that are not defined everywhere over the integral, over the interval. Here is one very example for which Gaussian-Chebyshev quadrature is very well suited. If you want to integrate that interval, if you make a plot of this function, then the function is not defined at the endpoints. You could see this again as a way to approximate pi, but notice that in order to define your Chebyshev quadrature, your points actually in the formula already use pi. So it's like you put a pi in the oven and you get a pi back. So the input of Chebyshev quadrature, you actually are already using pi. So you could see this as another way to approximate pi. So the question is here, apply this Gauss-Chebyshev quadrature rule to this problem here. It's a scary looking improper integral, but Gauss-Chebyshev should give you very high accuracy. All right, then, let us conclude our excursion into differentiation and integration. So we are closing off a chapter, but we move into ordinary differential equations, and we will solve ordinary differential equations by differentiation and integration. So what will follow in the remaining lectures are just applications of what we have solved so far. And in a way, the entire point of this sequence of 4 lectures was to apply interpolation, which does not work well for differentiation. So in extrapolation was the main idea of how to compute accurately approximations of derivatives. The quadrature rules are based on interpolation, weighted sums of function evaluations where the weights are integrals of Lagrange polynomials. We can improve the results of composite trapezoidal rules by extrapolation. We called it Romberg integration. And then for today, we saw that with Gaussian quadrature rules, we can get very accurate results using orthogonality and getting a very high degree of precision. So we will see applications of the main principles, the main ideas that we have covered in this lecture and in this chapter.